In this section, we introduce a temporal convolutional network. Temporal convolution network is a conventional-based sequence modeling method designed to capture temporal dependencies using causal and dilated convolutions. Unlike recurrent models such as LSTM, TCN processes an entire input sequence in parallel, which significantly improves training efficiency and leads to more stable gradient propagation over long time horizons. In practice, compared with LSTM, TCN typically achieves faster training, avoids hidden state propagation over time, and exhibits better numerical stability. Here, we show a typical TCN framework. Let's look at the internal structure of the causal dilated convolution layers. In this example, the network consists of three one-dimensional convolutional hidden layers. First, notice the input sequence on the left. The key property of causal convolution is that the output at any time step depends only on the current and past inputs, and never on future values. For example, when computing the output corresponding to t-2, the convolution kernel only accepts inputs from t-2, t-3, or early time steps, but never attach the t-1 or t. This strict temporal ordering ensures that the model respects physical causality, which is essential for time series forecasting tasks. The filter size determines how many consecutive time steps are involved in each local convolution operation. A filter size of 2 means that each output is computed using 2 input samples at a time. Next, we focus on the concept of dilated convolution. The dilation factor controls the spacing between input elements used by the convolution kernel or filter. When the dilation factor is 1, the convolution operates on consecutive time steps. As the dilation factor increases to 2 or 4, the kernel skips intermediate points and directly connects distant time steps. This design allows the receptive field of the network to grow exponentially with steps, enabling the model to capture non-range temporal dependencies without significantly increasing the number of parameters or weights. In practice, each convolutional layer contains multiple channels. Each channel corresponds to a different set of convolutional filters, which enables the network to learn diverse temporal patterns simultaneously. After the causal dilated convolution layers, a global average polling layer is applied. This layer computes the average value along the time dimension for each channel, effectively summarizing each feature map into a single scalar. As a result, the output of the polling layer is a fixed Nernst feature vector, whose dimension equals the number of channels. Finally, a fully connected layer maps the pooled feature vector to the output space. The output dimension is determined by the forecasting tasks, such as single-step or multi-step prediction. Now let's look at how to use TCN for power forecasting. An autoregressive structure is still used, as this approach provides high data utilization efficiency, and the overall forecasting procedure is similar to the previous case. Note, TCN doesn't rely on timestamp feature and hidden state propagation. Here is the results for TCN in a day ahead power forecasting task. The results show that while TCN achieves acceptable prediction accuracy, its performance advantage over MLP is limited due to the short forecasting horizon and the small training dataset. However, TCN exhibits the lowest training time among the previous methods, indicating the best computational efficiency in this case. For the next section, we will go to a new section and continue to introduce the forecasting methods suitable for the limited sample scenarios.